Hello everyone. In today's video, I want to give you the very essence of our method, the Approximate Gaussian Variance Inference, or in short, AGVI. Now, we can use AGVI in order to quantify aleatory uncertainties that are inherent in data. And we can do it online, meaning that we can refine our knowledge of the uncertainties as we see each new data point. Now, to see how the AGVI method works, let's take a simple sine-like function. For example, the black line shows the function here, the red dots represent the data, and the violet region shows the aleatory uncertainty that is present in this data. Now, a variance parameter is used in order to quantify what is the aleatory uncertainty in the data. Now, if we choose a larger value for the variance, this means that we'll be underfitting our model, and if we choose a smaller value for the variance, we'll be overfitting our model. And this is not what we want. We want to identify what is the correct variance parameter that can quantify the exact aleatory uncertainty present in this data. Now let's just remove the function and look at the residuals alone. Now this violet region over here represent the aleatory uncertainty. Now the residuals can be assumed to be coming from a Gaussian distribution with mean 0 and variance parameter sigma square. Now, if we have all the residuals available to us, we can use the empirical variance formula in order to compute our empirical variance. In this case, since mu is 0, let's cancel it out and we'll end up with this formula over here. Now, this is basically taking the average of all the wi square. So if I take square of all the residual terms here and we take an average, we get our empirical variance. And if we have large number of samples, meaning that t goes to infinity, then this empirical variance formula will tend towards the theoretical value, which is the expected value of w squared. However, this procedure is neither Bayesian nor online, because for this formula to work, we need to have all the residuals available to us. However, if we want to do it online, meaning that we do not have access to all the data points and we are observing one data point at a time, we can only start with a broad prior knowledge for the expected value of w squared, since we do not have good understanding of what should be the correct distribution for the expected value of w squared. So let's keep this distribution over here and I'll come back to it. So we have observed the first data point over here. Now using the prior for the expected value of w squared, I can obtain posterior for the w. Now if you look at the formula here, sigma square is equal to expected value of w squared, and w is now a Gaussian random variable having this distribution over here. So we still need to obtain what is, or how can we obtain the distribution for w squared. In our group, we have developed this approach called the Gaussian multiplicative approximation, or GMA, that can provide a closed form solution for this, meaning that we can obtain the expected value, the variance, and the covariance terms for the product of any two Gaussian random variables. Hence, using GMA, we can obtain a posterior for w squared now using the posterior for w. We have also found out a way to connect w squared to expected value of w squared, meaning that once we obtain a posterior for w squared, we can obtain a posterior for the expected value of w squared. Now, if you look at the figure over here, we started with a prior, and now we have this posterior. So there's hardly any difference between both the distribution. This is because we have only witnessed or observed one data point, and there is hardly any information to learn from just one data point. However, when we will see multiple data points, you'll see that the distribution for the expected value of w squared is moving towards the correct value, which is denoted in red dotted points, as well as the uncertainty is decreasing. And when we'll reach the end of the time series, it has correctly converged to what is the correct value for the expected value of w squared, as well as the distribution is a direct, meaning that there is negligible uncertainty associated with it. Also from the data here, you can see that in the beginning, since we started with a broad prior, so we have a large uncertainty over here. But as we see data points and reach the end of the time series, we have identified what is the correct aleatory uncertainty present in the data. Now, in this framework, we have connected, basically we have two steps where we connected w to w squared using GMA, and from w squared to expected value of w squared. This framework we refer to as the Approximate Gaussian Variance Inference, or AGVI. AGVI is a Bayesian method, and we can perform online inference for the error variance parameters that quantifies the elitary uncertainty that are inherent in the data. And the best part is that all the computations involved, going from W to W square or from W square to expected value of W square, we can do it analytically, meaning using closed form algebraic expressions. Now, of course, the devil is in the detail, so all the proofs, the formulation, the derivations are provided in our paper, as well as the code for this method, as well as different examples are available in GitHub from our official group's repository. Thank you.